Hello, my name is Vaibhav Lohia. I am a second year student in DSF branch in IIT Roorkee. Today I would like to present you to the topic linear regression in accordance with applied linear algebra. So let's start. First of all, let me introduce you what is the meaning of linear regression. Linear regression is nothing but a technique for determining the statistical relationship between two or more variables. Simply putting it together, we have to find a line that almost fits all the data points which we feed to it so that we can predict what will be the next data point in accordance to our input. It is of two types, simple linear regression and multivariable linear regression. In simple linear regression, we just have one feature, and in multivariable linear regression, we have more than one feature. Let me give you a easy example. Like if like we have cost of houses and we also have measure of the houses written. So the measure of the houses will be our feature and the cost of the house will be our output. Here we have only one feature, but if we have cost of the houses which we have to predict, and in feature we can have dimension of the house. Also, is it a 3 BHK or 2 BHK? Is it in posh location or not? And etc. etc. So if we increase the number of features, it comes under the category of multivariable regression. And in simple linear regression, we only have one feature and we have to predict the outcome. So what is an hypothesis? Hypothesis is nothing but the equation of the line for which we have to find. And we can also write it write it in this form. This form. And so the all story in linear regression revolves about cost function. And what is a cost function? Cost function. Cost function nothing but cost function nothing but this formula. And in this formula, the h theta x is our predicted value and the y is our actual value. And we have to minimize the error between them and we take their L2 norm. In order to minimize theta, we have a algorithm which is known as gradient descent. It basically works as that we we feed we feed the we feed new variable its old value minus some constant into the derivative of the cost function with respect to the feature which we are updating. Here alpha is known as learning rate. See, this is the thing which I was talking about, that we update the weight which is which is equal to the weight minus some constant in learning rate into the derivative of the cost function with respect to the weight. For simpler understanding, let's think about our h of x is a linear function theta 1x. We are neglecting theta naught and theta 2 for simpler understanding. So our cost function will be nothing but this theta 1x minus y and 1 by 2 is just a constant. So our graph will look like this because j theta is some square function. So it will be parabolic, and let's say we have to find this theta minimum. So first of all, let's initialize our theta naught. So our theta naught would be something like here. I initialize it here. So by updating its value, theta 1 would be smaller than theta naught because this thing is positive, slope is positive, and we are subtracting some positive value from some positive value. So we will get a value which is less than this. So we will be approaching towards the minimum theta. And once we approach to the minimum theta, our our d by d theta of j theta will become zero. As the slopes become zero, hence we get our theta minimum. And you might be wondering what is the case when the slope is negative. Not, the case is the similar because the derivative of the function of the j theta will be negative will be negative. So our theta 1 would be greater than theta naught. If we start from here, where here is the theta naught, so we would be approaching towards minimum. As you can see that our theta 1 will be getting theta naught, so we'll be approaching towards the minimum. So here I can summarize gradient descent algorithm with respect to the cost function and the features. Here, as we approach the minimum, our steps become smaller and more concise. We can, this is because the slope slope becomes smaller as we approach the minimum. We can also write it in matrix form, which will be easier to comprehend. Here, x is our input feature, which I talked about earlier, and y is our actual value of the respective feature, and h of x is nothing but the equation theta naught plus theta 1x plus theta 2 dot 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 plus some constant. We can write it in this form. Subtracting the predicted minus actual value, we get this matrix. And we also know that in vectors, we can write z square as z transpose z, where z is a vector. In similar manner, we can write x theta minus y square equal to this x theta minus y transpose into x theta minus y, where I'm taking the value of m equal to 1 in the cost function. So the cost function becomes like this. Taking the gradient of the cost function, first we take the transpose of the whole equation and then multiply it with this part. We get this. And by simply taking the gradient in the following step, we get the gradient of j theta equals this. This is a simple calculation, you can do it. So we want to find theta, which is equal to x transpose x inverse into x transpose into y vector, the actual values. This part we can call it as pseudo inverse, and this x transpose x inverse can be only done in overdetermined and determined systems, because in underdetermined systems this part x transpose, let me write in another slide, x trans x transpose x is invertible, is non-invertible, non-invertible for underdetermined systems. This is so because let's take an example of an undetermined system. Let's say we have a matrix A which have dimension 3 cross 2. Sorry. Taking its transpose, we get 2 cross 3. So A transpose A would be 2 cross 2. Hmm, wait a minute. No, no, no. Let's take 2 cross 3. Yeah. This will be an undetermined system. It will become, what am I doing? 3 cross 2. So A transpose A will become 3 cross 3. Rank of, as we know that rank of a matrix is less than the minimum of its column and its rows. And we also know that rank of A is equal to rank of A transpose A is equal to the rank of A transpose. So let's assume the rank of A matrix is 2. So the rank of A transpose A matrix will also be equal to 2. But as A transpose A matrix is 3 cross 3, so somewhere there would be a zero eigenvalue. So we can say that A transpose A is non-invertible. But if we take A transpose in place of A transpose A, we will get 2 cross 2 matrix, and we can use this in undetermined systems. We will see this later. We were thinking how to proceed in undetermined systems. We introduce a new value called the Lagrangian multipliers. What does Lagrangian multipliers do? It enforces additional constant like we have in this. So taking the derivative with respect to x and with respect to mu in this equation, if we take the gradient with respect to x, we get x vector as minus A transpose mu vector. Similarly, taking gradient with respect to mu, we get mu vector as minus A transpose inverse B vector. We can see that calculation. This is very easy. So if we take the optimal case that x vector equal to x star and mu vector equal to mu star, we get optimal x is equal to A transpose into A transpose inverse B vector. And this part can be called pseudo inverse for underdetermined case. So summarizing what I've taught, I can say that this is the this is the main function, this is the pseudo inverse. Pseudo inverse for determinate system is simply equal to A inverse. For overdetermined system is equal to A transpose A inverse into A transpose. For underdetermined systems, we get A transpose into A transpose inverse. So this was the whole about linear regression. So let's talk about the limitations of linear regression. There are mainly four limitations of linear regression. Four main uh, problems in linear regression. The first, that is linearity. We assume that we have a linear relationship uh, between features and the output, but there can also be a polynomial relationship between them. Also, sometimes we get the cases where the observations aren't proportional to the features, where we have a danger that we can overfit the data, which could give bad results. Also, outliers are problematic in linear regressions, and because they might cause an error. And also multicollinearity is also one of the limitations. In this, we doesn't have features which are we have features which are interrelated and not independent, so they can also cause problems. So now we see a code in which I have predicted house prices in accordance to the input. Let me let me show you the code related to gradient descent. Here we import libraries NumPy for numerical Python and Matplotlib for plotting purposes, where we randomize x and y. Here, this is the this part is the gradient descent functions, where we create a list, where we create an empty list, and we fill that empty list by x dot theta, where theta is the column vector of the slope and the intercept. Here we find the error. Here it is gradient, and there is we update theta cost function, and then we get the cost function, and then it returns theta and cost history. Here we get the testing x. Here we perform the gradient descent on testing x, y, and learning rate, which is depend on an iteration, which is 100. Here we create the uh, code for the plot. This is for the regression line plot, and this is for the cost function plot. Here we get the point of the iterations. Here we get the best fitted line, and here it is the uh, it is the cost function which is minimized after 28 iteration. It becomes constant, and this is the minimum value of the cost function. Thank you. Also, we get the optimal intercept and flow, which is 4.14 and 3.309.